Welcome to AP Chemistry. In this video, we will discuss the trends of ionization energy, electron affinity, and atomic size on the periodic table. Recall that potential energy is a measurement of a system's possible energy, while kinetic energy refers to its actual energy. Potential energy measures attractions and repulsions. When attractions are stronger, potential energy becomes more negative. And when repulsions are stronger, potential energy becomes more positive. Furthermore, the electron being attracted and bound to the nucleus is in a negative potential energy well, similar to how we are bound in reference to the Earth. In order for the electron to become less attracted, that is, to have a less negative or more positive potential energy, the electron must absorb kinetic energy. Finally, when an electron is at zero potential energy, the electron is no longer attracted or bound to the nucleus, and the atom has become ionized. Ionization energy is therefore the kinetic energy required to ionize an atom. Since it refers to an energy requirement, energy must be absorbed into the system. The change in energy for a given system, therefore, must be a positive value. Now, viewing the data provided, there are several distinct trends concerning ionization energy that we can relate to the periodic table. The first trend, of 5, refers to the only trend that will decrease the potential energy of our electrons. That is, increase the attractions between the electrons and the nucleus. The result is that more energy will be required to ionize that electron. Ionization energy will increase. This trend is noticeable when comparing ionization energies across a period on the periodic table. So, why does ionization energy generally increase across a period of the periodic table? The main difference from one atom to the next is their atomic number. That is, their number of protons. As the number of protons, or effective nuclear charge, increases, there will be a greater electrostatic attraction between the electrons and the nucleus. This will result in a decrease in the potential energy of our electrons, and an increase in the required kinetic energy to ionize those electrons, an increase in ionization energy. However, the next 4 trends will actually result in an increase in the potential energy of the electron. That is, a decrease in attraction between the electrons and the nucleus. Since the potential energy of the electron is higher in these next 4 trends, the kinetic energy required to ionize those electrons will be less, or a lower ionization energy. The first most noticeable drop in ionization energy is after the end of a period, at the beginning of a new energy level. Electrons are limited in their spacing around the atom, just as we are held up from falling through the ground by the electron-electron repulsions that occur between our feet and the substances that make up the ground. So also electrons cannot fit into a lower energy level once that energy level is filled. They simply would repel one another. This is referred to as the Pauli exclusion principle. Therefore, the electron takes the lowest energy position available to it in a higher energy level. However, when an electron begins in this new energy level, the electron is by definition farther from the nucleus, and thereby less attracted to it. The potential energy of the electron has gone up, and therefore the kinetic energy required to ionize that electron, its ionization energy, has substantially gone down. Thus, just as the potential energy of an electron increases when it begins a new energy level, so also when it begins a new sublevel. That is, from S to P to D to F. However, the reason is somewhat different. You should be aware by now that 2p is of higher energy than 2s, and 3d higher than 3p, higher than 3s. This should be a given according to the Aufbau principle when completing electron configurations. However, the reason is a bit nuanced. A 2p orbital, by virtue of its shape, occupies only one region around the nucleus, whereas a 2s orbital occupies two regions. Although the 2s orbital extends further outward than 2p, it actually penetrates the nucleus more substantially than 2p. Therefore, 2s is on average closer to the nucleus than 2p, and therefore of lesser energy than 2p. This trend of greater penetration in 3s than in 3p than in 3d holds true for all successive sublevels of a given energy level. The trend is thus termed the penetration effect, in which sublevels, due to their increased penetration into the nucleus, result in greater attraction to the nucleus. Higher sublevels thereby have less penetration and less attraction, and therefore increased energy. The next trend for increased potential energy in our electron is a subtle one, occurring when a sublevel's orbitals are half filled. Recall that according to Hund's rule, electrons take the lowest possible energy state by filling each orbital first before pairing. This is simply to reduce the amount of possible electron-electron repulsions when electrons become paired. However, once each orbital has been singly filled, the next electron does pair with an opposite magnetic spin. But this does not come without cost. Due to electron-electron repulsions, the paired electrons are now in a higher potential energy state, decreasing the amount of kinetic energy required to ionize them. That is, their ionization energy. Although somewhat tangential, it is important to note that ionization energy does not generally drop when entering the D block. As we have discussed in class, uh, in reference to potassium and calcium, nature initially fills 4s first. That is because 4s is initially lower in energy than 3d. How is this possible? This is because 4s actually penetrates the nucleus much better than 3d, and given the number of protons with potassium and calcium, 3D is not actually accessible yet. So we see in potassium and calcium that 4s is filled. But then with a sufficient number of protons, we are now able to access 3D. And 3D is lower in energy than 4s. But this then shields 4s from attraction or increased attraction to the nucleus. And so we can see the general effect across the transition metals, across the D block, is that the 4s energy level doesn't really change that much. And therefore, the ionization energies are all pretty much similar. The last periodic trend refers to the trend of comparing ionization energies down a group. As more energy levels are layered on top of the nucleus, a shielding effect occurs, in which lower energy level electrons shield higher energy level electrons from the effective positive nuclear charge. The attraction, now weaker, valence electrons have higher potential energy, and less kinetic energy is required to ionize them. Finally, if we compare successive ionization energies, that is, the first ionization energy to the second to the third, or the first amount of energy required to ionize compared to the second required to ionize compared to the third, we will always see a general increase of energy required to ionize in succession. This is because once ionized, the atom, now ion, will have an overall positive electric charge, creating a much greater attraction or hold on the remaining electrons. Generally, the trend doubles in successive ionization energies. However, the trend becomes much more pronounced, at least 5 times fold, once an electron is removed from a lower energy level. You can see this by the values underlined in red. Now, it may seem like a daunting task to learn a whole set of trends, and not only for one phenomenon, but for multiple. However, the same 5 trends that we have just discussed for ionization energy also underline the trends for electron affinity, but in a different application. Therefore, it is imperative that you understand the reasoning behind the phenomena. Remember, oversimplification always leads to overcomplication, but complexity, when comprehended, leads to the simplicity of the wise. So, what then is electron affinity? If ionization energy is the kinetic energy that must be absorbed to remove an electron, a positive change in energy, then electron affinity refers to the kinetic energy that must be released in order to add an electron, a negative change in energy. Therefore, note again the general trend across the periodic table. As the number of protons increase, there will be a greater affinity for electrons. That is, a greater amount of kinetic energy will be released when adding an electron. It is important to note that electron affinities are commonly reported in absolute value, as shown here. But all of these values must be used with a negative sign when actually completing their calculations. Again, the reason for why more kinetic energy is released is due to a greater drop in potential energy of the electron when that electron becomes added to the atom. Like a satellite decreasing in potential energy as it falls to the Earth and releases kinetic energy to its surroundings, so also will the electron generate increased movement, kinetic energy, in the surrounding particles. The other 4 trends of increasing potential energy in relation to the electron, new energy levels, new sublevels, half-filled sublevels, and shielding down a group, all apply to electron affinity as well, but in distinctly different ways. Note, for instance, how electron affinity drops at group 18, whereas ionization energy dropped in group 1, for exactly the same reason. Ionization energy dropped in group 1 because less kinetic energy was required to remove the electron that existed in a new, higher energy level. However, electron affinity drops in group 18 because less kinetic energy is released when adding a new electron to a new higher energy level. Therefore, the same applies for starting a new sublevel. Whereas ionization energies dropped in group 13 due to a higher energy sublevel, so also electron affinities drop in group 2 for the same reason. Again, ionization energies dropped in group 16 due to greater electron-electron repulsions that exist, but electron affinities drop in group 15 due to greater electron-electron repulsions that would result with the addition of another electron. The last trend of electron affinities, concerning shielding, clearly has some exceptions. The trend should be that electron affinities decrease due to decreased attraction down a group. However, there are notable exceptions in the p block. This has to do with another important trend occurring simultaneously, that of the size of second energy elements. They are simply too incredibly small. The addition of electrons generate substantial electron-electron repulsions in these small atoms, which yield weaker than expected electron affinities for these elements. Be sure to familiarize yourself with every aspect of this chart, as well as to know where the drops in both ionization energy and electron affinity occur on the periodic table. These relationships are both essential in themselves and foundational for later dynamics and chemical bonding that we will shortly discuss. The trends in relation to atomic size are much more straightforward, incorporating only three of the ones that we have discussed. As you can clearly see, across a period, as electrostatic attraction increases, atomic size decreases. However, as a higher energy level is begun, the electron's distance from the nucleus substantially increases, and therefore atomic size is increased. The last trend refers to progression down a group, as electron shielding becomes more pronounced. Here, we see a general increase in atomic size as well. Finally, it is important to note what effect ionization will have upon size. A greater net positive electric charge, such as in the case of cations, will result in a much smaller size due to the net pull being towards the nucleus. However, a greater net negative electric charge, such as in anions, will result in a much larger size due to the net pull being away from the nucleus, in the direction of the orbiting electrons.